Hi everybody, and welcome back to Napkin Math. In today's video, I'm going to be talking about whether you should buy a hybrid car or the plug-in version of that hybrid car. And so recently I've been considering buying a new car, and two of the cars in the lineup were a hybrid car and the same car, but the plug-in hybrid version. And I was talking to my friends and family about some of the considerations, and one of them said that they wouldn't buy the plug-in version if they weren't within the electric range of the car because it would not be saving them as much gasoline, or that they would still need to be buying gasoline anyways, and the inconvenience of having to charge the thing would be outweighing the benefits. Now, I took issue with this statement pretty quickly, so let's think about that. So first, let's assume that the plug-in hybrid that we're talking about has 30 miles of electric range, meaning that the car can travel 30 miles just on the electricity, and then it will switch over to its gasoline engine and behave similarly to a hybrid car to travel the rest of the distance. So in that case, if you're at home, and here's your house, so you wake up and you need to get to work. So you wake up, you unplug your plug-in hybrid, and you travel 30 miles. Let's say you live 30 miles from work in this case. So you travel the 30 miles to work, meaning that you saved 30 miles worth of gasoline getting from home to work. Then at work, let's say you can charge at work as well. So you plug in your car, you work, and then you're ready to go home, and you commute another 30 miles back home. Another 30 miles back home. And once again, because your plug-in hybrid has 30 miles worth of electric range, you save 30 miles worth of gasoline. And in grand total then, for that day, you saved 60 miles worth of gasoline. Now, let's consider the case where you live far away from work. So once again, you have a home, but now you live 100 miles from work. So you wake up and you need to commute 100 miles, not drawn to scale, 100 miles from home to work. Your plug-in hybrid only has 30 miles worth of electric range. So it only saves the first 30 miles of travel, and then it runs out of juice and becomes similar to a normal hybrid for the remaining 70 miles to work. And then at work, you charge again, and you need to commute back home. So you commute back home, once again, 100 miles total, but you only save the first 30 miles back. So the grand total number of miles worth of gasoline that you saved is, once again, 60 miles. So at this point, you can probably tell what my issue is with the original statement that you shouldn't buy the plug-in hybrid if you live outside of its electric range. We can see that in both of the cases outlined here, we save the same miles worth of gasoline. So this was the initial motivation for this video, although these two examples don't quite cover the entire picture for whether or not you should go for the plug-in over the normal hybrid. So I do want to go even deeper and try now to construct a function that represents the savings that the plug-in will give you, or the lack of savings. So let's go into that. Alright, so before we even dive in, I want to go over the variables that will be considered by this function. Now, you don't need to pay too close of attention here. I'm going to try to recap what each of these is as I use them later on, but I want to just, as an introduction here, talk about everything that we're going to consider in this function. So let's just list off some variables here. So one thing to consider, like just efficiency aside and everything, will be the price differences between the cars, because often you're going to find that the plug-in is more expensive than the hybrid. So we're going to call P sub H the price of our hybrid, and P sub P the price of our plug-in hybrid. And then we're also going to consider the cost of gasoline. So P sub gas will be the cost of 1 gallon of gasoline in the area that we're considering. And similarly, the cost of electricity is also going to be a factor in this because, unfortunately, unlike the simplistic overview I gave before, electricity is not free, and you don't just magically save those electric miles for free. So P sub kWh, standing for kilowatt hour, is going to be the price of 1 kilowatt hour in dollars. Both of these are going to be in dollars. The price of gas, actually all of these are going to be in dollars. Price of everything is in dollars. And we also need to consider the efficiency burning gas of each of the cars, right? Because it's possible that the miles per gallon in hybrid mode, if you will differ between the two cars. So we're going to call M sub H the miles per gallon, if you will, of the hybrid car. And I'm just going to wrap around and do like a new column here. We're going to call M sub P the miles per gallon of the plug-in variant of the car. And of course, as we saw in my previous example, something that is very important to this function, or at least that may be very important to this function, is going to be the distance between home and work. And we're just going to call the distance D. And then another thing to consider, of course, that we already talked about is the range of the plug-in hybrid in electric mode. So how far can it get on a full charge of its battery? We'll call that R sub P. That's the range of the plug-in. And then we also need to consider the efficiency in electric mode of the plug-in hybrid, right? How many kilowatt hours from my house, like how many kilowatt hours am I adding to my electric bill per mile driven by this plug-in in electric mode? Because once again, electricity is not free, and we're going to have to factor in how wasteful the electric portion of the trip is. So we're going to call K sub P, this is one of the more confusing variables, K sub P is going to be the number of kilowatt hours used in order to travel a mile, right? The number of kilowatt hours used per mile by the plug-in hybrid in electric mode. That is what K sub P is. And then finally, finishing up on the last couple here, we'll want to talk about, or at least it'll come into play, is length of ownership. And we're going to consider this in days. So we're going to call that just L sub ownership. L sub own. And that is just, again, the length in days that you own the car. Oops. And then finally, and this one's also important and a little bit confusing, I suppose, is whether or not you can charge in both locations. Because if you can only charge at one of the two locations, you just intuitively, you can think that that's going to limit how much electric range you get to benefit from on your day's journey there. So I don't have a nice name for this. We'll just call it, it's a Boolean really. It's like either yes or no. So can charge at both. And in fact, because I don't want to keep having to write that, I'm going to write that as just C from basically now on. But again, so C will end up being like 1 in the case that you can in fact charge both at home and at work, and then it will be 0 or like false, right? Because 1 is like true if you're computer science land, and 0 is like false. So C will be 0 in the case where you can only charge at one of the two locations. So that's just an overview of everything that this function will consider. There are things that the function is not going to consider because I have no damn idea how to deal with them, like, for instance, the tire wear or brake wear or things like that. I think that goes a little bit too far. But yeah, so this is this list of variables that I'm going to be considering. Alright, damn, that's long, huh? So let's play then. Now that we've kind of defined our terms here, we can begin to play the fun game. So the first consideration that pops out to me is going to be the distance from work, d. Like, sure, if you live further than the range of the plugin from work, then you're going to save the whole R sub p on that leg of travel, right? You're going to save that whole range of electric on each leg of travel if you live longer than the range of electric travel from work. But what if d, your distance from home to work, is less than R sub p, the electric range of the plugin? Then you won't be able to use all of your electric range on one leg, and so you may actually be saving fewer miles worth of gasoline on that leg than you could have, since there are literally just fewer miles traveled. Right, so let's sketch this out just a little bit here. So if d, the distance from home to work, is greater than the electric range of the plugin, then as we saw in our introductory example, then you're going to use the entirety of this electric range on your commute, because your commute on one leg is longer than your electric range. But it gets weird when d is less than R sub p, because now all of a sudden you're not actually going to use all of R sub p before you end up getting to work. So let's just summarize that observation. What we're really talking about there is the savings in miles on like one leg of travel. So we'll just call that savings on one leg, which is a function of your electric range, R sub p, and d, the distance between home and work. And so we can see that when d is larger, we get R sub p. So we get the smaller one of the two if d is bigger. And then we can see that if d is less than R sub p, then the savings is going to just be d on that one leg, right? So in both cases, we're actually taking the smaller of the two, which means that this is actually just, easily enough, the minimum of the two variables, like that. And in fact, calling this function savings on one leg is a bit misleading, right? Because what we were actually talking about is the number of miles you traveled electrically on one leg. So let's just go ahead and rename this thing to electric miles on one leg, because that's a more apt name. Alright, so that's cute. We have this little function that tells us the electric miles we can travel on one leg of the journey. The problem is there's two legs on the journey, so we gotta dive into that. And we are almost just going to toss this function, but it'll actually come up a little bit here. So, I mean, we know that like min R sub p and d is the electric miles traveled on one leg. But because we have two legs, we need to now bring into the picture whether or not you can charge at both locations. Because if you can only charge at one location, if you're close to work or far away from work, things are going to get weird between the two legs. Not too weird, but a little bit weird. So let's just break this down. Let's say that can charge at both, which I renamed to C, is true. So you do in fact have the ability to plug this thing in both at home and at work. So in this case, it's actually quite easy to think about, right? As we just constructed, we know that on one of those legs, you're going to get the min of the electric range and d, electric miles, out of that leg. So really, our savings for both legs is just, well, it's two legs, so 2 times the min of R sub p and d. So again, so when can charge at both is true, we have twice the min of R sub p and d. Easy enough. But now we must consider when you cannot charge at both. So you can only charge either at work or at home, but only one of them, and not both of them. So now we need to think about this, right? If you charge at home only, and let's say that the distance to work is less than your electric range, so in that case, you're not going to use all your electric range going from home to work, and you'll have a little bit left over to use on that second leg, right? You can see how a scenario like that can come up. And so what are we really being limited by here? Well, you can consider that on both legs of the journey, well, on each leg of the journey, you're going to travel a distance d. So on both legs of the journey combined, you're going to travel a distance of 2 times d, right? And you could only charge at one of the two locations. So at most, in a given day, you're going to save, if you have infinite electric range on this plug-in hybrid, right, you're going to save 2 times d miles using electric power, right? And that 2 times d will only be limited by the electric range of the vehicle on one charge. So what we're really talking about in the case where you can only charge at one is the minimum of the range of the electric vehicle and 2 times d. Because remember, we're constructing a function now that will magically tell us the number of electrically traveled miles on both legs. And so in the case where you can only charge at one of the two places, one of the two destinations, you could travel at most a distance of 2 times d. So certainly you cannot save more miles, or you cannot electrically travel more miles in a day than you need to travel. And another limiter is going to be the range you get out of one charge, or R sub p. Because you also can't travel more than the range of the electric vehicle, R sub p, in a given day when you can only charge one time in a given day. Alright, so we've gotten the makings here, the function that will tell us the electric miles driven in a given day on both legs of our journey between home and work. But we can see here that it's like conditional on whether or not you can charge at both places. So when C is true, it's one function, and when C is false, it's kind of a slightly different function there. So we need some way to combine these into one function, or at least it'd be ideal if we could combine these into one function mathematically. And we actually can, without just, casing it out like, oh, well, in the case that C is true, you do this, and in the case that C is false, you do this. We can actually wrap it up into just like a nice one-liner, if you will, using some tricks with the multiplication by 1 and 0. So when C is true, as briefly previously mentioned, it's 1, right? And when C is false, it's 0. So we can kind of use that 1 or 0 as a selector for either calculating this, aka multiplying that by 1, or if C is 0, then multiply that by 1. And so we can use that as a way to select them appropriately based on the value of C. Right, and it'll end up looking something of the form C times the true function, because then if C is 1, it'll be 1 times the true function, which means whatever the true function is. Or we could also take 1 minus C times, which is kind of like the opposite of C, if you will, times the false function, because when C is 0, then you can see that this little term here when c is 0 is just going to be 1, so you will actually consider taking the false function if c is 0. But when c is 1, that term will be 1 minus 1 and will be 0, so you will ignore the false function and then only be taking 1 times the true function. So that's kind of how the trick works there. So we can go ahead then and plug in the true and false function to get the result that we desire. So it'll end up being c times our true function, which was just twice the min of r sub p and d, plus the opposite of c, 1 minus c, times the false function, which is the min of r sub p and twice d, like so. And then, of course, with that, we should probably give that function a name of some sort. So, again, this function really represents the miles traveled electrically by the plug-in hybrid in a given day, so on both legs of the journey. So let's just call it electric miles on both legs. And that is a function of, well, we have r sub p still, we have d, and we have c. Alright, so now we're definitely getting somewhere here, because we have this magic function that will tell us how many miles we can travel electrically on both legs, or in a given day, however you really want to look at it. And with this function, we can begin to play games converting this into some kind of a cost saved, right? Because these electric miles would have had to otherwise be spent if we had the hybrid car just burning gas, right? If the hybrid car had to travel these electric miles, then it had to burn gas to do that. And it only has a certain efficiency in miles per gallon, right? And so if we know that we have electric miles on both legs, electric miles to be saved, and we know that the hybrid would have otherwise had to travel those miles at an efficiency of m sub h miles per gallon, then we can just take that and divide by m sub h, and that will give us the number of gallons that the hybrid car would have had to spend to travel those otherwise electric miles. So that's in a sense what we've just constructed is the number of gallons of gas we just saved on both legs. And so if we saved that many gallons on both legs because we were able to drive them electrically, and we just multiply that by the price of gas per gallon, right? Gallons saved times price of gas per gallon. That gives us an actual dollar amount now that we saved in electric mode, not having to burn that gasoline. All right, so that's nice. Let's just rewrite that real quick for sanity's sake, okay? So let's call the function, shall we, well, we're approaching the cost saved per day here. So we're going to call it cost saved per day. So we'll say cost saved per day. And this is a function of, well, everything that electric miles on both legs needs. So r sub p, d, that's a d, and c, whether or not you can charge it both. And then we've also introduced now the mileage of the hybrid a bit, and the price of gas. Piece of gas. So with all those variables, we've got a function. Let me just scroll down a little bit here. That is, as we saw, the electric miles on both legs and it takes in its variables, divided by m sub h, the mileage of the hybrid, the miles per gallon of the hybrid, times the price of gas. Like so. Cool. So we're done then, right? That's it. We have a function that gives us the dollar amount we've saved per day, and we must be done. And this function must be perfect. Well, no. Electricity is not free. Just because we were able to travel electric miles on both legs electrically doesn't mean we actually literally got them for free. What we've computed here is really the price that it would have cost the hybrid to also commute those miles. But we're assuming that we've saved all of that money, but it's really more like we've saved all of that money minus the cost of the electricity to travel those miles. So we need, right? You can imagine we need some kind of a term over here that's like, oh yeah, minus the electricity. Like electricity cost. We need something like that on this right-hand side to get more accurate here, more down to earth. So let's figure out what the electricity cost would be. So yeah, I mean, we just said that, or we already know that, electric miles on both legs represents how many miles we traveled electrically. So that's a good starting point. So we know that we traveled electric miles on both legs. How's that for a nice long function name? So we know that that tells us the number of electric miles that we traveled. So now we need to consider how much those miles cost us. So recall that at the beginning of the video I mentioned a magic variable k sub p, and k sub p was the kilowatt hours, conveniently enough, the kilowatt hours per mile used by the car. And even more than that, it really represents the kilowatt hours that were required from your household to charge that battery to travel 1 mile. So that's really a nice, conveniently defined variable, because if I just multiply the number of electric miles by that magically defined k sub p, then what I've got is really the number of kilowatt hours used for those miles. So that's nice. And once I've got that, I think it's fairly obvious that number of kilowatt hours used times price per kilowatt hour gives you price overall. So if you just multiply this by the price per kilowatt hour, which previously defined, P sub kWh, price per each kilowatt hour, we can see that really that thing right there is our electricity cost mentioned above. Alright, great. But at this point you're probably like, whoa. You can't just conveniently define k sub p like that. We don't have access to that information, k sub p. This function's going to be useless if we don't know what the hell k sub p is. So we gotta figure out k sub p real quick. So, I mean, let's think about it, right? K sub p is supposed to be a measure of the kilowatt hours used from your house to travel a mile. So, kilowatt hours used to travel a mile. Now, car manufacturers are going to tell you a couple of important pieces of data. They're going to tell you the battery capacity, first of all, and that's going to be in kilowatt hours. We'll just call that VC, and that's going to be in kilowatt hours. So again, that's like the size or the capacity of the battery itself that's in the plug-in hybrid vehicle. And we also are told a range, again, R sub P previously defined, the range of the plug-in hybrid in electric mode, and that's just in miles, right? So if we know that we can travel R sub P miles electrically, and electrically we have a battery capacity that is also known in kilowatt hours, then the kilowatt hours used per mile by this car to travel on its battery can be thought of, so k sub p, that magical variable, can be thought of as the battery capacity in kilowatt hours divided by R sub P, the range of the vehicle in miles, because that's kilowatt hours per mile. Kilowatt hours is on the top, miles are on the bottom. There's one little final thing here, because I think it's a little bit disingenuous to just assume that the household charging is like 100% efficient. So if you want to consider the charging and efficiency, right, let's say that the charging efficiency is only 80%, so only 80% of the kilowatt hours used at your house actually make it into this battery pack when you're charging. That would change this case of P, and you need to account for that multiplying the denominator by 0.8 in the case of 80%, right? So that's like efficiency from household kilowatt hours into battery pack kilowatt hours. And so yeah, case of P is not just complete voodoo magic. You can figure it out using this little equation if you'd like. Alright, so let's recap again here. This is all nice information. I'm not actually going to substitute in that case of P equation. I'm just going to leave a case of P for brevity. But so let's recap our function here now that we know the electricity cost. So cost saved per day. Okay, so we have something like cost saved per day is now, I'm not going to write all these, is now more along the lines of the electric miles saved per day electric miles on both legs, again, some variables there, over M sub H. So again, this is like gallons the hybrid would have had to spend on those miles, times the price of gas. And then now we have to subtract away the cost of the electricity that we got there. So simply minus electric miles on both legs. Some variables times K sub P that we just talked about. And that is kilowatt hours, so times the price per kilowatt hour, P kWh. Okay, so this is looking a bit better. We've now considered some gas savings and the cost of electricity for that supposed perfect savings. So we're done, right? Well, let's look at what we've got so far here. So we're saying with this first term, because we have a plug-in hybrid, we've traveled some number of miles electrically that the normal hybrid would have had to burn gas to do. And so in this first term, we're just assuming that those electric miles are basically free, and we're saying, okay, so the hybrid would have had to pay this much to travel those free miles, so our cost saved per day is the amount that the hybrid would have had to pay to travel those electric miles. But then we considered in the second term that, okay, those electric miles weren't quite free, so it's more like that savings, if we assumed that the electric miles were free, but then you have to subtract from the savings the cost of the electricity to actually travel those electric miles. So that's nice, But let's consider what we're not yet considering here. We've been talking only about electric miles so far, but what about those non-electric miles, right? Like, let's draw a quick little picture with the home ordeal again. Here's our house, and you're going to travel to work. So far in our equation here, we've considered the electric miles, right? So we said, I think in our toy example, we said something like 30 miles out of the total 100 miles, right? So right now, we've only been focusing on like, okay, this will save us some amount of money, right? And the hybrid, of course, would have just been burning gas, like on the entire range of 100 miles, the hybrid would have been burning gas, and we have been talking about savings thanks to that electric portion of our trip. But there's more than just the electric portion, right? What about all of this? That is a non-electric portion for which both the plug-in hybrid and the normal hybrid need to be burning gasoline to complete. And they burn gasoline at different efficiencies. And the plug-in hybrid generally is going to be a heavier car than the normal hybrid. So I would, intuitively expect that heavier car means a little bit worse gas mileage. And at least in the cars that I'm thinking about, that holds true. So we do need to consider that, again, in this toy example where it's like 100 miles, 30 miles, there's an extra 70 miles there where both the hybrid and the plug-in hybrid are going to be in gas mode to complete the trip. And the normal hybrid very well may have a higher efficiency at burning gas than the plug-in hybrid. Alright, so really we're trying to construct like another term for our cost saved per day function that's going to represent for us any extra money that we're going to lose because our plug-in hybrid happens to be less efficient on the gas portion. So let's start there. First of all, what is the distance that we're concerning ourselves with here? And it's actually going to just be d, well, 2 times d, right? That's like the total distance that we're going to travel in the whole day on both legs, and that's not subject to change. And then minus the electric miles that we were able to travel on both legs, which we already have a magical function for. With a very long name that is very appropriate because it tells us exactly what the function is doing. So this little term here in parens is telling us the miles for which both of these cars are traveling in gasoline mode and for which we need to be comparing the miles per gallon efficiency between the two cars. Okay, had to reorganize there real quick because I ran out of space to keep writing. Anyways, so we've got that both the plug-in hybrid and the hybrid are going to need to travel this distance here in gas mode, right? Both cars need to go that many miles in gas mode in a given day. So what we can do then is begin to discuss how many gallons of gas is it going to cost each car to be doing that. Just briefly, I'm going to actually rename this little variable, or call this whole thing just miles, just so I don't have to keep rewriting. So if we take miles and we divide it by the miles per gallon of the hybrid, what we've got is the number of gallons of gas that the hybrid would take, right? That's the gallons hybrid would take in order to travel those gas miles that we're talking about. And similarly then, if we take miles and we divide it by the mileage of the plug-in in gas mode, we get the gallons that the plug-in is going to take in order to complete those shared gasoline miles. So first of all, we expect that the plug-in is going to be taking more gallons because it's less efficient when it's in its gasoline burning mode than the hybrid is, simply because it probably weighs more and some other things like that. So we can just do a quick subtraction then, like miles over MP minus miles over MH, and that's going to give us like how many more gallons the plug-in takes than the hybrid in order to complete that shared gas portion of the trip. And you know, this may be 0. If they have the literal equivalent MPG when they're both in their gas burning modes, then this term could be 0, and that would be fine. But in general, that little expression is going to be representing for us how many more gallons it took the plug-in to complete the shared gas miles. So gallons times price per gallon is going to give us the additional cost incurred on those gasoline miles by the plug-in. So all we have to do is multiply by the price of gas as previously defined. And then, so that little term that we've constructed is now representing how much more, if at all, it cost for us to complete the definitely gas portion of the trip if we're driving in the plug-in versus if we were driving in the hybrid. So that's the extra cost of the plug-in to complete the gas miles. And you can actually see, you know, like miles is common to both, so you can actually just factor miles out of that box there, or out of those parentheses. So we can clean this up just a little bit. Let's just do it for sanity. So it'll be miles times 1 over MP minus 1 over MH, like that. And then, you know, times the price of gas. And so that's the term we've actually constructed there. So finally, we should consider now subtracting this again from that cost savings function, right? Because this is, again, a potential additional cost that the plug-in hybrid is going to cost us. And, you know, you might be considering like, well, whoa, what if the assumption doesn't hold true that the plug-in has a worse miles per gallon than the hybrid? And actually, it doesn't matter, right? Because then you'll be, if we subtract the yellow box there from our cost savings function, and it turns out that the plug-in is somehow actually better MPG in gas mode than the hybrid, then you'll be subtracting a negative and therefore actually adding to your cost savings function. So that would be fine. So I'm going to go ahead and incorporate all this into the function, and I'll save you the trouble of watching me write it all out. Alright, so this is what we are left with then. If we take all that stuff and mush it back together into our costSavePerDay function. So let's just take one nice last look at this function in depth, where we look at the first term here. So this first term, again, is considering that, okay, with the plug-in hybrid, we travel some number of miles electrically that the hybrid would have had to burn gas on. And so this first term is representing the cost of the gas the hybrid would have had to burn on the electric miles that we got. And we say, okay, that's like our cost save per day, but oh yeah, we have to also consider that the electric miles were not free, they cost that much. So subtract from our savings the actual cost of the electricity to go those electric miles. And then finally, we consider, okay, this third term, there may be some shared gasoline-only portion of the trip for which both the hybrid and the plug-in hybrid are burning gas. And for that stretch, we need to consider that their miles per gallon may be different. And so this third term captures any additional cost caused by driving the plug-in hybrid instead of the hybrid over that shared gas stretch. So I mean, this function is already very useful to us, right? You can imagine that now you can work out how many days you're actually driving to work, and then compute kind of like a weekly, monthly, or yearly savings by just multiplying the cost saved per day by however many days you work in a year. So yeah, we can do stuff like that now with this function. So this one's already very useful. It gives us the literal dollars saved per day. So if we were to have had the plug-in hybrid instead of the normal hybrid. And you can also actually use this function, as some of you may have noticed, you know, the hybrid car is just a car which burns gas at some mpg efficiency. You know what else is just a car that burns gas at some mpg efficiency? Literally every gas-powered car. So it doesn't actually have to be a hybrid that you're using this to compare the plug-in to. This function can compare the plug-in to any other non-plug-in gas-using car. So it's quite nice as it is, actually. So are we done? Well, not quite. Hold on. I want to take this one little step further because I think it'll nicely wrap up the usefulness of this function. So I want to construct a new simple function that uses this cost saved per day. And you'll remember previously I already introduced variables for the length of ownership and the price of the plug-in and the price of the hybrid. So I just want to use those real quick. So L sub own, or the length of the ownership in days, can be used with this cost saved per day function to compute the cost saved over the length of ownership of the car, right? And we can do that very easily. Cost saved per day with some parameters and times the length of ownership in days. And that is some sort of a cost saved for the length of ownership of the car. And so if you're looking at like cost saved over the entire ownership of the car compared to the hybrid, right? Because really we want to find out, like, should I buy the plug-in? Is the plug-in a good deal over the hybrid? So over the life of the plug-in car, is it going to save me money as compared to the hybrid car? And so we know that, well, on the day-to-day basis, in terms of like getting to work and back, we're going to save over the life of the car cost saved per day times L sub own, dollars, right? So we save that many dollars, and once we've got that nice number, we can just start subtracting away other differences that you may wish to consider. So anything that's not included here, and one example is like the price difference, because usually the plug-in hybrid will end up costing more. So P sub P, the cost of the plug-in hybrid, minus P sub H, the cost of the hybrid. So that's the additional cost of the plug-in car over the normal hybrid car. You just subtract that from your cost saved over the life of ownership of the plug-in car compared to the hybrid car, and this will give you sort of a cost saved just overall for the life of the car if you go with the plug-in option instead of the hybrid option. So then you can, like, if this number is positive, that basically means you should get the plug-in hybrid over the hybrid, and if it's negative, then that means you'd be losing money to get the plug-in hybrid instead of the hybrid. And you know, this is great because you can take this further if you'd like, because is my function perfect? No. Did I forget to consider some things? Probably. There's things like that are not easy to capture in a function because they vary so much over place or the cars that you're talking about. So you could consider like depreciation over the length of ownership, and you consider additional brake wear, additional tire wear, because the plug-in might be a heavier car, right? So you can now kind of easily account for any of those things by just in your head making a guesstimation, like, oh, okay, well, X thing is going to make the plug-in cost another $100 over the life of its ownership as compared to the hybrid. So you just subtract 100, and you can just do that for literally any possible other expense that you can think of. And so yeah, I think that ties it all together here nicely. You guys can take this further as you wish. Any additional cost you could possibly think of the plugin having, you can just add a subtraction term at the end to account for it. And so, I mean, that about does it for this video. I mean, I hope you guys have at least had fun following along and learning along here with me. But I'm gonna probably make a tool to plug in values for this function so that you guys can plug in your own values for where you live, like the cost of gas and the cost of electricity and things like that, and see the result. And I'll also even before I do that, I'll just whip it up in Desmos, a very nice tool, by the way. Go Google Desmos if you haven't seen it yet. But yeah, so you'll be able to plug in values at least there and see some graphs too of what this function looks like. And I mean, I've already done that, and the link to the Desmos graph will be in the description. So check the description for that link to the Desmos graph if you would like to play with it. And also the link to any tool I make will eventually end up in the description. But in general, the function ends up looking something like, I mean, obviously it's a function of many variables, right? So you have to fix most of them, and usually I fix all of them except for x, or sorry, except for d, the distance you have to travel from home to work. Because remember, coming into this, my initial motivation was to find out, like, what really is the dependence on the distance from work in terms of the value proposition of a plug-in hybrid. And you know, the graph tends to have a behavior kind of as follows. So again, so x-axis is d, increasing in that direction, and y-axis is savings in dollars, you know, increasing up the y-axis. So what you find, at least what I found for the cars I was comparing, was that you usually, in most cases, you see something like this. And this is the case where the cars being compared are such that the plug-in obviously has some electric range, but then the hybrid has a better MPG. And so as the distance from your workplace increases, after a point, because of that worse MPG on the gas stretch, you start to suffer actually having the plug-in versus the hybrid. And you're like, okay, well, what is this, like here we're making some good savings, right? What is this peak? And this peak is actually when you live exactly R sub P distance from your workplace, because that means you're taking full advantage every day of the most possible range that you could. So when you take full advantage of that electric range, you get the most savings. So yeah, this is the usual case where it's like the plug-in electric is better up until you start surpassing its meaningful range on electricity. And so other cases I saw, so if it's the case that the plug-in has better miles per gallon, just even on gas, compared to the car that you're comparing it against, then you'll actually end up seeing a graph more like this, where it's like, okay, obviously benefiting, then you hit a point, and then you benefit less, but are still benefiting. And that makes a lot of sense, right? Because as you drop this down onto the distance, the x-axis there, you're using electric range up to a point, and then after that point, you're less efficient, but still, like, you're less efficient than if you were still driving on electricity in terms of cost, but you're still more efficient in terms of cost than driving on the even worse miles per gallon hybrid or gas car. And so you're still actually benefiting no matter what, no matter your distance, because you're just better, you're a better car in every respect than the car being compared to. So yeah, so that was kind of the behavior of the graph when P sub P is greater than, or sorry, not P sub P, when the miles per gallon, so the M sub P, the miles per gallon of the plug-in in gas mode, is better than the miles per gallon of the hybrid in gas mode. So yeah, you would see that in that case. And then finally, the last possible case is when electricity begins to get very expensive. It's possible, right, that gas is actually just so cheap compared to electricity that you should never be charging your car on electricity. And in that case, you see a graph where it's always detrimental to have the plug-in compared to the hybrid, and you see something like that. So yeah, I mean, that's, again, so that's really the case when electricity is just so expensive that it'd be cheaper to like burn gas instead of using electricity, which I don't think is the case almost anywhere, at least in the United States. But if that were the case, then you should just get the most fuel efficient MPG-wise car that you can, right? And so the plug-in is losing because, so yeah, so this is the case when electricity is high in cost, and the miles per gallon of the plug-in is less than the miles per gallon of the car that it is being compared to. Then it's just like you should never buy that plug-in because it's bad in every scenario. Okay, and then one more graph that I thought of here, and this is actually the one that I was kind of, you'll remember in the initial toy example, this is the graph that I was kind of expecting to see, where when I was thinking like, oh well, after a certain distance from work, your benefits should just be the same, right? And that is actually the case with this function if you graph it. Man, that's a bad straight line, huh? Okay, well, that is basically the case with this function if you graph it when the miles per gallon between the two is just equivalent, right? So if the miles per gallon efficiency of the plug-in was actually equal to the miles per gallon of the hybrid, then what you'd see with this function is that up to a certain distance from work, you'll benefit, you'll increasingly benefit having the plug-in over the hybrid, because you're getting to more and more utilize that electric range. And then once you've capped out your electric range usage, you're still benefiting, but not by an increasing amount, because you can only save as much as you get to drive electrically in this case. And so that was the final interesting case I wanted to just mention there real quick. But yeah, so that is the end of the video. I hope that you liked it. I hope you had fun, and maybe this function will actually be useful to someone out there. Feel free to play with the tools that will be linked in the description, and I will see you next time.